This presentation is delivered by the Stanford Center for Professional Development.
Great. I guess we're on. So we didn't get very far. We just started talking about the basic ideas of barrier methods, but we'll really do it today. So we'll look at how it all works. Okay. So the idea actually is very simple. Maybe if you can go down to the pad here. You start by rewriting the problem. You take the constraints and you simply put them this way. It's f0 plus, there we go, plus, and then this is, I minus is the indicator set of negative reals. And so I minus is this function that's 0 and then goes to plus infinity if you're above 0. And this is, of course, this encodes the semantics of a hard constraint. It basically says you have no irritation if it's less than or equal to 0. And if it's positive, you are infinitely irritated, meaning that that x is completely unacceptable. So this, I mean, we can then say, look, it's just an equality constraint problem here. But of course, this is just rewriting things. And it doesn't really help anything. Because this function, it is true the only constraint now is an equality constraint, but this function, of course, is highly non-differentiable. And because we put this here, that's exactly the point. Okay, so what we're going to do is we're basically going to replace this indicator function with an approximation of the indicator function that's smooth. So, and this is, I mean, many ways to talk, a lot of people talk about this. It's something like this. When I'm making fun of people who propose things like this, I usually say that this is the same as getting out some sandpaper and saying, you don't like this corner here, so you sand off the corner or something like that. So we talked about this at the end of last lecture. So a very common approximation is the log barrier. So the log barrier goes like this. You have the sum of the logs of the negatives f's. Obviously, if f becomes 0 or positive, this goes to minus infinity, and with the minus sign, it goes to plus infinity. It's a barrier. And you put a 1 over t in front. T is going to be a parameter that controls how close this thing approximates this indicator function. And it's important to understand the trade-off here. The trade-off is this. The larger t is, the closer this function looks to that. That's clear. But that's both good and bad. It means that by solving this problem, you get, well, we hope, it means, we'll see soon, it is true, that you're getting a closer and closer approximation of this problem. It certainly means that. But on the other hand, the larger t is, and the more this function looks sort of like this one, where it's just basically this indicator function with the corner sanded down, that's going to mean this is a harder problem to solve using Newton's method. Okay? So that's going to be the trade-off here. And we'll see how that how it works around it. So that's the idea, is that we're going to solve this using Newton's method. By the way, there's nothing wrong with solving this with Newton's method. We know how to solve that. Any value of t, you have a feasible point. We can actually, a strictly feasible point, Newton's method will work perfectly on this. There's just no problem. Okay, so this function here, which is the sum of the minus log of the minus function, of the minus constraint functions, is called the logarithmic barrier function associated with the constraints. So that's the log barrier. And this minus log minus f, that's a convex function by one of these composition rules, because minus log minus something is an increasing function and so on. Increasing and convex, and then f is convex as well, of course. So that's convex. It's a log barrier, and you can get a rough idea of what it is. For example, another way to say it is this. It's minus the log of the product of the minus fi's. So these are slacks, because that's literally how much extra you have in the inequality fi of x less than 0. So minus fi is the slack. And this is negative log the product of the slacks. So that'll come up a bunch of times. Okay. For the record, we'll work out what the derivatives are. So the gradient is simply this, because that's just a composition rule for the log. And the Hessian looks something like this. It's got these rank 1 terms here, and then it's got these things with a scaled version of the Hessians of the individual functions. Okay, so that's the These are the gradient Hessian. We'll come back to this. Actually, we'll need the gradient very soon. All right. Now, when you minimize f0 plus 1 over t phi of x, it's the same as minimizing tf0 plus phi of x. It's the same thing. And when you minimize this, we'll actually refer to the minimum of this as x star, the argmin, as x star of t. So that's going to be it's the minimizer of this function subject to that. And we'll call that x star of t. And we're just going to assume here that there's a unique minimum, and we'll call it x star of t. Well, we'll get into that later. Actually, if the sublevel sets are bounded, there's a unique minimum. But we'll just leave. We'll just say this is the minimizers, x star of t. This is a function of t, of course, and it traces out a curve, a path, and that's called the central path of this optimization problem. So you call that the central path, and the intuition is something like this: as t goes to infinity, you would sort of guess that x star of t is going to go to an optimal point of the original optimization problem, because as x star of t goes to infinity, the difference between this thing and this, I have to include the minus sign there, the difference between this and this basically goes away, because as t goes to, certainly element-wise, point-wise, well, except for at 0, but element-wise, it's fair to say that this thing converges to that as t goes to infinity. So you sort of guess that this is the case. And here's an example for an LP. This is an LP in R2, of course, so it's kind of silly. But you've got some inequalities here. I guess 1, 2, 3, 4, 5, 6 inequalities like that. And then these dashed curves show you the sublevel sets of the barrier function. That's this thing, like that. That's the sublevel set of the barrier function. And you can see the one in the middle. That's with t equals 0. You minimize the log barrier. By the way, that's the same as maximizing the slacks, the product of the slacks, or the geometric mean of the slacks. So that's actually called the analytic center of this polyhedron, and that's right there. And then as you increase t now, what happens is you're incentivized to, well, let's talk about what phi does. Phi is a barrier, and what this does is it wants to keep you away from the boundaries. Because if you get near a boundary, one of the fi's is going to be negative but near 0. That means one of the minus fi is going to be small, one of the log of that is going to be big and negative, and with the minus sign it's going to be big and positive. So this barrier function, if you can visualize it, goes something like this. It's got its minimum there, and then I guess it curves smoothly up. It's an analytic function. It curves smoothly up, and then when it hits these walls, it goes to infinity. So you should visualize that here. Now, when you crank up t, what happens is, by the way, you'll never find a point that is outside the interior of the feasible set, because this thing, the domain of this, is the interior of the feasible set. So no matter how high t goes, you will always have a point that is interior. And by the way, that's why one of the names for these things is interior point methods. We'll see later, actually, that modern interior point methods don't work this way anymore, but still, the name has stuck, and that's why they're called interior point methods. Because every point you produce is in the interior. That used to be the case anyway. Okay, so what happens is you crank up t, and you're going to move more and more towards, if t is this c, you're going to move, this is the curve, that's the central path, and you can see that as t goes to infinity, you approach this optimal point. Okay, and that's the picture. That's how this works. By the way, so far you should be deeply skeptical of all this because, well, for the reasons I talked about last time, but I'll talk about them again. Let's see. The other thing I should mention is that this is this is sort of a famous method. There's a general class of methods that work that way, and they're called homotopy methods, like this. And I can sort of explain a little bit about how these work. A homotopy method works like this. You have a problem that you want to solve, but it's hard, and you don't know how to solve it, or something like that. What you do is you make a parameter. You then you introduce a parameterized family of problems, parameterized by, let's say, a parameter t, let's say, and you arrange for the problem to be easily solved when t has some value like 0. In this case, it's just you've already written code to do that like 2 homeworks ago or something like that. So it's simple to find this analytic center. Then what happens is as you crank the parameter, the problem you're solving is going to transform into the one you want to solve. So in this case, that happens, roughly speaking, as t goes to infinity. So a homotopy method works like this. You have a parameter value, you solve the problem, then you crank up the parameter a little bit and solve it again. Hopefully, starting from where you started before. That should work. Hopefully that works or whatever. If it doesn't work, then maybe you were too aggressive in your t update or something like that and you back off. Or, I mean, you can think of all sorts of methods for this. By the way, these methods are very widely used. I mean, all over the place. So that's that's what this is. I'll come back to that. Okay. Now let's actually do some, let's see what happens on the central path. Well, if you solve this problem, then it means that the gradient of this plus A transpose nu is 0. That's the dual residual being 0. And of course, AX equals B. So it means that the optimality condition for minimizing this barrier augmented problem is this. You have to have the gradient T grad F0 plus, and that's the gradient of the barrier, plus A transpose W equals 0 and AX equals B. So that's the optimality condition. Now, if you stare at this long enough, you'll look at it and you'll realize you've seen stuff like this before. And in fact, what you saw before is this. We can take this thing and we can divide by t. That's the first thing we'll do. Divide by t, like that. And then you stare at this long enough and you realize, well, these are just like positive numbers. So I'm going to call those just lambda I. And then you're going to look at this and say, wait a minute, this is grad f0 plus some lambda I grad fi plus A transpose times something equals 0. And you realize, like, wow, look at this. If you define lambda I this way, this equality means that if you're on the central path, you actually minimize the Lagrangian with this value of lambda, this value right here. Okay? So that's the picture. Okay, that's great. If you minimize the Lagrangian, then it means you actually have a point that's dual feasible. That's what it means. And that means immediately you're going to get a lower bound on the original optimization problem. So let's see what happens. It's actually kind of interesting. It says, if you minimize this, which, by the way, you can do very easily for any value of t. This is Newton's method to minimize this. But if you minimize this, then actually, whether you like it or not, you will actually get a dual feasible point for the original problem. That's what's going to happen. So you're going to minimize that. You're going to get, when you finish, you're going to get this. You're going to define lambda I as minus 1 over t fi of x, like this. That'll be lambda I. And you'll get a dual feasible point. And then, of course, you have a dual feasible point. You want to evaluate g. That's the dual function at that point. And you work that out. So I'm going to plug in this lambda into g. Now, g is nothing but this. It's f0. I don't have it written here, but I'll write it out. It's going to be f0 of x plus some lambda I fi of x. Well, and then it's plus nu transpose ax minus b, but that's going to be 0. So I'm just going to plug in the lambda I found. This is going to be g of lambda. It's going to be that. But the lambda I, this thing, is minus 1 over t fi of x. Okay? This f cancels that. That's a sum over the constraints. So this is equal to f0 of x plus, here, that's all the same number. So it's actually, let's see, the lambda I is that. So I get actually, it looks like to me, minus m over t, period. Okay? Now that's very interesting. It says that if x minimizes this thing, that's something you can do by Newton's method, then I also inadvertently calculated a dual feasible point, and that gave me the following lower bound. And that tells me the following, that the optimal value of this problem is clearly, has the following property. Certainly, it's less than f of, I have a feasible point, x. So the optimal value is clearly less than that. But it's bigger than g of lambda. But g of lambda is this, f0 of x minus m over t. Well, it's beautiful. You know what that says? It says that if you minimize this function here, which is a completely smooth function. So you just, that's Newton's method here. If you minimize this, the solution will be no more than m over t suboptimal for the original problem. Okay? So now you have the hard proof that, in fact, as t goes to infinity, you actually compute an optimal point. In fact, it's much more. The truth is that as you solve this problem and vary t, you can say much more. You can say the following. When you solve this problem, you will produce not just a primal feasible point, you will produce a dual feasible point, and you'll really produce a primal dual feasible pair. And the gap associated with that pair, the duality gap, the difference between the primal value and the dual value, will be exactly m over t. So that's what this means. You had a question?
Should g of lambda be an infimum of the right-hand side instead of f0 of x?
What's that?
Oh.
Should the right hand? Should the
G of lambda should be infimum of right-hand side over x, so that g of.
Oh yeah, sorry, but yeah, the reason x my x minimizes the Lagrangian. You know how I know that? I know that because this is the optimality condition for minimizing the Lagrangian for this choice of lambdas. So I do know that it minimizes. This is the, if I plug in my x star, it does give the infimum over x of the Lagrangian. I don't know if that made sense. It was a.
Where did m come from?
Where m is the number of constraints. Right. So this is very. This is pretty cool. And by the way, there's a method. There's a method for solving the original. We already have our first method, by the way, for using Newton's method to solve a constrained problem. And in fact, it's got a name. We'll see why it's called that in the later. It's called. So the name of this method is called UMT. We'll see later because that's a takeoff on a name that later we're going to see. SUMT, which is sequential. So I'll tell you what this is. This is sequential unconstrained minimization technique. But and I like the name. I'll tell you why. It's kind of a retro name because it points out that everything we're doing so far was actually known in the 60s. And so when you mention this name, it's sort of a reminder, because if you type this into Google, well, actually, if you type this into Google, you'll probably get a lecture I wrote. But if below that, you'll find whole books on this in the 60s. That irritates the people who imagine that all of this was done in the last 15 years. So, and that's why I like to use the term. So this is the unconstrained minimization technique, and it works like this. It's really dumb. Watch this. You want to solve this constrained problem. Minimize f0 of x subject to fi of x is less than 0, and ax is equal to b. The UMT method says this. Pick t and solve the following problem. I'm assuming here, by the way, you have a strictly feasible starting point. We'll talk about how to get one if you don't. It says minimize this. f0 of x plus 1 over t times minus sum minus, log minus fi. Okay? That is a smooth function. Newton's method will minimize it. Well, I should say, certainly in theory, it will, I mean, so will the gradient method, by the way, in theory, minimize it. But the point is, you can minimize this. When you minimize this, you will have a point that is feasible here. Actually, it'll be strictly feasible. And you will also, you can absolutely guarantee that you are no more than m over t suboptimal. So you might say, done. That's it. We're just done. Pick your tolerance. You want 1e minus 6 tolerance. Pick t equals whatever it is, 10 to the 6 times m or something like that. End of story. In theory, that's actually correct. So Newton's method, just one shot does it. So this is, we'll actually see. It's more when you combine this with the homotopy idea that you actually start getting methods that are both A, practical, and B, pass muster with our complexity theory friends. Okay? So that's how that describes the S. By the way, you shouldn't make fun of the UMT because there's plenty of practical applications where it's entirely appropriate to just pick a value of t, minimize that, end of story.
On the previous yellow sheet where you wrote the dual function, I was wondering how you got ax minus b 0.
Oh, because look, ax equals b is part of the optimality condition,
Right, but
right?
It's going to 0, right?
No, it's not. No, it's 0. No, it's 0. Yes, I solved, here. I minimized, here it is. There we go. I solved that problem. And the constraint is AX equals B. So I assure you AX equals B. AX equals B is not negotiable here. We have a point that satisfies AX equals B. So, okay. Everybody got this? So this is, it's pretty simple. We're up to about 1967 here. Yes?
Add AX equals B there also?
To where? Oh, over here?
Yeah.
Well, I should, yes. You mean if I want it to be true?
Yeah.
Yeah, sure, whatever. Okay. Sure, there. Sure, these are details. You know you don't have to do that in a 300 level class, right? I mean, you can look, it's an official rule. I can switch a minus sign. There's some number above which you're not supposed to have, but I mean, it's expected. In fact, you wouldn't even want everything to be right here, would you? It'd be insulting. What is this, a 200 level class where, you know, so, but thanks for pointing it out. Okay. All right, so let's actually interpret this this stuff via KKT conditions, because you can, right? You can actually interpret it lots of other ways. Here's another one, and this one is also like quite cool. It's this. Let's take this is the point on the central path. That's so x star of t minimizes wherever it is. I've lost it. Here it is. It solves this problem here. Lambda star is the lambda defined by that. Let me point one thing out. When you fix t, you don't know lambda star until you've calculated x of t. So you don't know what dual point you're going to end up with until you do this. Curiously, though, you do know exactly what duality gap you're going to have. Your duality gap is going to be exactly m over t, period. So in fact, one way to say it is, when you solve this problem, which appears to be a primal problem, whether you like it or not, you're actually going to calculate a primal dual pair for the original inequality constrained problem with a duality gap exactly equal to m over t. That's what you're going to do. In fact, you can even think of t as a parameter, which m over t is clearly simply the duality gap. So you can literally dial in whatever duality gap you want and be done. Okay, and that would be the method. Okay, so let's look at this. Let's look again at what it means to be central. I should say that if you solve this problem, you would refer to a point like that as central, or on the central path, or centered would be another one. These are the names you would use for that. Okay. Well, here's what these points satisfy. Well, in fact, this one I can make stronger. You're actually strictly feasible, obviously, because in fact the objective that defines x star of t has log minus fi. So this is strictly positive, and in fact these are strictly positive. Okay, because those are 1 over t times minus fi, which is strictly positive. So those are positive. Okay. Now here's the cool part. The optimality condition. Well, this is our definition of what lambda I is. We actually get minus lambda I fi of x. This is if you're on the central path is equal to 1 over t. Now what's cool is the following. So we write down these conditions, and the optimality conditions for the original problem, inequality constrained, are really, really simple. And I'll draw them right now. Ready? It's just that. So that's true complementary slackness. Is this right? It says that lambda I fi is 0. So if in fact you have x and lambda that satisfy, well now I do have to change this back like that. Okay, these 1 through 4 with this 0 here, that is the exact KKT conditions for the original inequality constrained problem. Okay, if you're on the central path, you satisfy all 4 of these except 3 is modified from exact complementary slackness to approximate, and this is just 1 over t. So that's another way to say it, to say that when you have a point on the central path, you've actually found a set of points that satisfy 3 of the 4 KKT conditions, and the one where they come up short is complementary slackness. And in that one, instead of lambda I fi being like minus lambda I fi being 0, sorry, they're all equal to 1 over t. They're all equal and they're just 1 over t. So that's another interpretation. This is actually the most common interpretation these days of these methods. So if you look at books and things on these methods, they'll just start from KKT. Okay. Now, you can also think of this in terms of, there's a nice force field interpretation, and that's this. Forget the equality constraints to make it easy. Here's what happens. What we do is we have a force field here, which, well, we have a potential. So you think of this as a potential, and I'm going to think of each of these with the minus sign as a potential contributed by each constraint. So each constraint right now has a barrier function, but I'll think of that as a potential, which means it's a force field, and the gradient of the force field is going to be, of the potential is obviously the force. So that's the way I think of it. Now, what happens is this. The forces balance that's when you minimize the potential, the forces balance. And that means here that the force contributed by our objective here, so this is a force contributed by the way, this is the potential, this is the thing we want to minimize, is actually balanced by the forces of the contributed by the barriers. Now, the barrier forces actually have a beautiful interpretation. I mean, especially when you have linear constraints. That's the easiest thing, so I'm going to do that. So let me describe how it works there. So here, for linear constraints, sorry about that. Here's the way it works. My force field, my force field on top of this is simply in the direction c. By the way, if you like, you could make this gravity. So this could be g times whatever down. Okay, so that's what this is. So it's simply a constant force field in the direction minus c. That's what this force field is. That's the objective. So here's our point. Where's c? C is apparently this direction. So the force contributed by the objective is simply a constant force in this direction. It's pushing you towards values of low c transpose x, which is obviously what you want to do. Now, the force field associated with each log barrier term, well, you take the derivative of the log, and you get 1 over something. And it turns out it's exactly this. It's an inverse distance. It's a 1 over r force field. So this gives you a beautiful way to actually picture this, understand exactly how it works. Here's what you do. Take each constraint and spray it with some repellent. Okay? And the repellent has the following property. Wherever you are here, this plane will put a force on you. It will point away from the plane. That's the direction it will point in. And its magnitude will be actually exactly 1 over the distance to that plane. Everybody got that? So, by the way, there are no such repellents or whatever. I tried thinking of like some case in some number of dimensions where you could spray positive charge. No, there are none. But anyway, imagine there were such a thing. So you spray the, and this means, for example, if you're here, let's actually work out what the force field is there. You feel a very strong force from this plane, and you feel a very strong one from this one. You're about equidistant. Oh, by the way, what kind of force do you feel from these three? Much less. So basically, the force that you feel at this point is, in fact, someone tell me which way to draw it. Like this way? This way? This way? Let's like that, right? So basically, it goes like, it would be forced like that. By the way, that's actually good. That's where the barrier force is not fighting the objective. It's actually pointing you away, because you're at completely the wrong point. Okay? So, and you can actually imagine all sorts of things. Like, what if you get right up to one of these constraints? Which way is the force pointing? Well, it's basically pointing you away from the constraint. Okay? All right. Now, imagine if you now put no force on it. So in fact, what we'll do is we'll just make this in a plane. So this is actually just sitting level. And what happens now is the particle will settle to the analytic center. That's where all these forces balance. It'll be like, it'll be a point there or there. I don't know. It's somewhere in the center, right? Now actually, all I have to do is this. That's C. Let me see if I can get it right. Yeah, okay, so I think here's what you're going to do. Take this page and start tilting it, because that's exactly what you're doing, right? Because then you're putting more and more gravity force on it. And when you tilt it all the way, you have to be able to tilt it like, I guess, gravity has to be like way, way high here. But as you rotate this thing, what happens is there's a gravitational pull pulling this in this direction minus c. And it will move over a bit. For each angle, it will hang off to the, it'll hang down a little bit until the repulsive forces from these three counterbalance the gravity force. Everybody see this? Now as I crank the gravity force up super high, you're going to settle over to a point here. Of course, you won't be touching these, but you'll be very, very near. And you'll be pinned right up against the active constraints, near, but not actually touching the active constraints. And there, the repulsive forces will balance the attractive force generated by the objective. So, I mean, it goes without saying, none of this actually matters. This is just for you to have a feeling for how this works. Okay? Actually, let me just ask you a quick question to make sure you do get it. Let me ask you, suppose there was, how many constraints I get here? 1, 2, 3, 4, 5. All right, you know what? I'm going to put some more constraints. Ready? Like this. Ready? Tons of constraints like that. Like, let's say 10 of them. Okay? Now, let me point something out. The constraints I just added, they do not change the feasible set. So what's the optimal point? That's, of course, it's the same. It's right here. What does the central path look like now? Does it move? We haven't changed the feasible set. Has the central path moved? Where is it? Okay, what happens is these constraints, though they have no effect, they do not in any way change the feasible set, in any way. They are felt very strongly by this particle, because 1 over r is a very slowly decaying force field. And what happens is the central path, the central point is probably here, and this thing probably sneaks up on the optimal point that way. Why? Because it's feeling a repulsive force from all these things, even though they're outside the feasible set. Everybody see this? I mean, this doesn't matter, but it's sort of just to give you a feeling for this.
So as you tilt the plane, what is telling you to tilt it in the direction that actually falls the particle?
Because I want to put a gravitational force in the direction minus, I want to put a force in the direction c, minus c.
So c is going to determine how that
C will tell you how to tilt the table. Okay. Yeah, so you tilt it along c. Okay, so that's, okay. Now we're ready to tell you about the barrier method. So the barrier method is this. By the way, the other name, there's lots of names for it. SUMPT, I already told you one. Definitely you should try to use this because it's irritating to people who work on these things, and that's always good. So you should try to use this term. And you should also drop things like saying, oh, wasn't all that known in 1969? I'll tell you a story about this shortly. Okay, so, all right. So here it is. It's the barrier method, otherwise known as the SUMPT method. It's got other names too. It works like this. Ready? You start with a strictly feasible x. We'll talk about how to get one later. And some initial value of t, which is positive, and some parameter mu, and some tolerance. And here's how it works. You simply do centering steps. So you compute x star of t by minimizing this. And this could be using Newton's method. I mean, it doesn't really matter. But if you want a complexity method, and if you want this method to work well, you're going to have to use something like Newton's method here. Okay? So you do this. And you will start from the previous value, the previous x star found. Then you update x. Now, when you've computed x star of t, of course, your duality gap is exactly m over t. If m over t is less than your tolerance, you quit. And by the way, you would return, when you quit, you could actually return, both x star of t and lambda star of t. And in fact, it's considered polite, if you write a solver, in convex optimization, at least, it's considered polite to not just return a primal a nearly primal optimal point, but to also return a nearly dual optimal point with a duality gap that's less than some number, right? Because that way, in fact, it's anyone can check. They don't have to trust you, because in fact, if you've asked for a tolerance of epsilon, they return a primal and dual point. None of your business how they calculated x, lambda, and nu. Totally irrelevant. You just check the duality gap. And so they're actually returning both essentially the suboptimal point and the certificate proving that it's epsilon suboptimal. Okay? So you could do that here. And then you increase t, and you would multiply t by mu. Now, let me just say a little bit about this. So the stopping criterion, of course, is completely non-heuristic here, right? Because in fact, it returns not just a suboptimal point with some vague idea that it might be optimal if some unknown parameter was small enough or something like that, which is how most of these methods work. Instead, it returns not just a suboptimal point, but a certificate certifying its epsilon suboptimality. And here, you should imagine a trade-off in the choice of mu. So the trade-off would be something like this. Mu is how much you increase that parameter t in each step. You should imagine that things like 1.05, if you have 1.05, here's what should happen. Let's imagine you use Newton's method, because it's important to get the intuition behind it. If you use Newton's method, if mu is 1.25, 1.05, it should take maybe only 2 Newton steps to recalculate the new center, because basically you're at some point. Well, let me draw a picture here. Basically, here's what happens in. So here's your central path. You're right here. You've calculated that point. You crank up t by 5%, and you want to calculate this. But the point is, you just minimized a problem that was very, very similar. The truth is, where you're starting is nearly optimal anyway. And so so basically, in 2 steps of Newton's method, you should be right back here. Okay. Now the problem is, you only made 5% reduction in duality gap, because the duality gap is exactly m over t. If t went up by 1.05, your duality gap went down by 1.05. Of course, that means if you do it, I don't know, 100 times, it'll work pretty well, or something like that. So these are little mousy steps, and this is what you'd imagine. This is what a normal homotopy method is. A normal homotopy method, you should imagine little mouse steps, because that's what the homotopy method says. I have a parameter. I can solve this problem. I can't solve that problem. And what you do is you crank your parameter just a little tiny bit, and you make each step not too hard. And you hope, you pray to the god of Newton, whoever controls whichever gods control Newton's method and things like that, that this will converge in a couple of steps. That's a standard homotopy method. Okay. However, it turns out here, it's going to turn out that the actual updates are very aggressive that can be used. Oh, by the way, this model of little mouse steps is exactly what the complexity theorists will tell you to do. So if you want, later we're going to actually bound the total number of Newton steps required. And in fact, the complexity theory will require us to take mouse steps. They're on the order of something like, mu is going to be something like 1 plus and then 1 over square root of the problem size. Okay? That's what our complexity, and that choice of mu will optimize the overall bound on the number of Newton steps. Okay? In practice, it turns out the values of mu can be very aggressive. They can be things like 2, 5, 10, 50, depending on the problem. And these things will work very, very well. It's shocking. That's really no homotopy step. These are just huge aggressive steps. So if you crank it up by 10, it means that you're going from this point, your next point is going to be here. And your next point will be even closer. So what happens then is it might take you a bunch of Newton steps. So you're going to go you're going to have a whole bunch of Newton fun, and you're going to land up there. Okay? So this is not, a normal homotopy, right? Where normal homotopy is you crank. I'll give you an example of a homotopy. How many people here use SPICE? Well, so that's great. Just for the record, that was like no one, or anyway, no, there's a couple people. Okay, so to those people. So you know that in SPICE, one of the things you do is you have a nonlinear circuit, and you want to calculate the bias, the equilibrium point, the bias thing. Well, it's a set of horrible nonlinear equations. I mean, nobody, you can't solve it. And in fact, already you can even have big trouble if you have like bistable things, like if it's got memory or stuff like that. It's multiple equilibrium points, but you want to calculate an equilibrium point. All right, here's the way you do it. So again, addressed to those people. Let's take an amplifier or something like that. And the homotopy, you want to know what the homotopy parameter is? It's just fantastic. It's totally cool. Can anyone guess? Actually, I know a lot of you people have been tortured with it, because a bunch of you people are from EE. So don't hide. Don't think you can hide. I know a lot of you are in EE. You're in stat. You're safe. That group over there. Yeah, but the rest of you, there's no way. I mean, you've seen this stuff. All right. So the homotopy parameter is the supply voltage. Because take an amplifier, and let's set the supply voltage to 0. Anyone want to tell me what the voltage and currents in the circuit are? 0. Thank you. That was easy. Okay. And then I take the supply voltage. I'm ramping it up to, what's your favorite supply voltage? 15 volts. No, I know what he's talking about. That dates him. I mean, you're way too young. for that. That's crazy. So you're, that's like, I might say that, plus minus 15 volts. I can say that, but why can you say that? You can't say that.
Straight from Sedgwick and Smith.
Oh, Sedgwick and Smith. Because you read old stuff. Okay, fine. All right, no, 50, okay. No, your choices are 5. Depends on your age. Okay, or I guess the age of the people whose stuff you read. Okay, so it could be 5, 3.3, 2, down. Now, if you're really cool, you'd say like 1.1 or 0.8 if you're like super cool now, right? See, I knew people knew, and you're just holding out on. All right, doesn't matter. So what happens is this. So we take a big circuit, we set the supply voltage 0. Everyone agrees all voltage and currents are 0, right? Okay, now you set the supply voltage to 100 millivolts. All right, what happens if you take like a big, horrible digital logic circuit and set the supply voltage to 100 millivolts? By the way, how well does it work as a logic circuit? It doesn't work at all. Okay. However, can I calculate the bias point? Someone who you know this, right? Come on, you held back on me on the satellite stuff, even though you're from Harbin and should know this, right? You've had this circuit stuff? A little bit. Okay. All right. So take a logic circuit. VDD is 100 millivolts. What does the circuit look like? Yeah. Oh, very, very, very subthreshold, right? It looks like a resistor circuit. So we can solve it in 1 Newton step or 2, right? No problem. So you get these things because they're not even on. The transistors, they're not even on. I mean, it's ridiculous. They're not even transistors yet. They're resistors. Okay. Then you go to 200 millivolts. But you start from the one you just found, and then you go to 300, 400, whatever, and so on. And if you go, by the way, from 1 volt to 1.3 volts, and it fails to converge, then you go, oh, I'll try 1.15. Everybody got the idea? Anyway, so so there you go. That's a homotopy method. That's how SPICE works. Okay?
Is there any downside to using a large mu, like an aggressive
Here?
50 or something? Yeah.
Yeah. I'll tell you what the trade-off is. In a circuit problem, if you're trying to find the equilibrium, the downside is real simple. If you too aggressively update VDD, Newton's method, which is what is used to calculate the equilibrium position, will fail. It'll fail. It'll fail to converge. Okay? So that's the trade-off there. For us, we cannot fail because we solve a convex problem at every step. We cannot fail. You can crank mu up, T up to 10 to the 9. And at least the theory says we can't fail because we can minimize any smooth convex function with equality constraints, right? So we can't fail. But what can happen if you update T super aggressively? Remember our theory, we can trot out all our theorems and talk about numbers of steps and blah, blah, blah. What will happen is the number of steps will be just absolutely huge. But actually both in theory and in practice. So that's the problem.
We as in like in MATLAB.
We as in, yeah, MATLAB doesn't do anything. Let's remember that. Okay, they do nothing. Remember, LAPAC is doing the work. Don't forget that. Okay, yes?
The fact that the Newton method rolls over at some point, I can transition.
Exactly.
Do we use that to choose mu?
So that's very interesting. There are whole methods that actually do exactly this barrier method, and they choose mu so small that they can prove that when you update T by that amount, you're still in the region of quadratic convergence. So that's called a short step method. There are lots of them, and a lot of the proofs go that way. And basically it says you can prove that by cranking up T by this small amount, if you were in the region of quadratic convergence before, you will remain in it for the new value of T and so on. So that's one way. No, I can tell you how we pick the update. Well, I can tell you a reasonable way to pick it. Actually, how you will pick it. Ready? Mu equals 2. There. Here, I'll pick another one. Mu equals 10. How about mu equals 30? These are sort of the numbers that work. There's much more complicated ways if you get into ultra high-end ones. By the way, they don't do a whole lot better, honestly, than these simple things. That's the embarrassing part. So you can get 50 papers written on how to update this parameter. Right. I mean, some of these are quite fancy and effective, at least for some problems. But so this is just empirically, this appears to be the right, anywhere between 2 and 50 seems to be the right number. Okay. And there's lots of heuristics for the choice of T0. By the way, this is something that's discussed in the in the book. You should actually read about that. T0 actually implicitly is the original duality, your original duality gap. So that's what T0, M over T0 is your original duality gap. So if you had some reason to believe that your current point was suboptimal by 5, then it says a reasonable value of T0 is on the order of 1 over 5m or something like that. That would be a reasonable one. That would give you the same duality gap and you'd just center. Okay. So let's do the convergence analysis. To show that it works is actually kind of silly. I mean, we know that, but we can say a lot of things. Now, the number of outer steps, by the way, the outer steps here are called, these are called centering steps or outer iterations or I don't know, whatever it is, right? So, by the way, it should be clear that you don't need to do that this is all, there's lots of stuff you could save here. For example, when you do a centering step, you don't need to like polish off, you don't have to compute x star of t to 16 significant figures. That's totally clear because in fact this whole thing is just a method to guide you towards the solution, right? So you don't have to do full centering. But I mean with Newton's method it's cheap, it's a couple of Newton steps, and the difference between getting an okay solution and an unbelievably accurate solution, an amazingly accurate solution is two or three steps in Newton's method, so there's no reason to worry about it too much. But okay, so there's a lot of stuff here you can imagine is not, can be shaped off, but for an algorithm that's very short to write, it's amazing how well it works. Okay, so how does this work? Well, the number of steps is, you can say the exact number. It's very simple. It's just log of, it's log of m over epsilon 0. Every time, the duality gap after the first step will be exactly m over T0. Then each time you do an outer step, that shrinks by a factor of mu. So you can immediately just work out the exact number. It's this. That's the number of steps it's going to take. And that's a ceiling of these things. Okay? So that's the number of outer steps it takes, period. Notice it has nothing to do with anything but T0 and epsilon and m. Nothing else. Okay. Now, the centering problem, and let's look at how this varies with mu. If mu is big, this number is kind of small. If mu is like a little mouse step, like 1.01, this number is big, right? I mean, if mu is 1.01, log mu is 0.01. So basically, that's 100 in the numerator here, right? That's basically what this is. So, what's that? No. Log 1.01 is 0.01, kind of. Very close, right? So, am I wrong? No. Okay, all right. So, okay. Okay, so that correctly reflects the variation in the number of outer steps is monotone decreasing in mu. So mu is your update aggression parameter, aggressiveness parameter, and that says that the more aggressive you are, the more duality gap reduction you get per step. So you take fewer outer steps. Now the problem is, the more aggressive you are in your update, the harder the problems you're solving by Newton's method. So, now you can do this intuitively and just say, therefore, what we should do for our problem class is just try this out, adjust various, solve giant families of problems. Oh, by the way, Newton's method cannot fail. So we have a proof that Newton's method will converge and so on and so forth. And if you use the classical analysis, it would involve all sorts of constants that you don't know. But it doesn't matter. You would at least have, at that point, a conceptual proof of convergence, right? Which would be to say this method can't fail or something. So that's fine. But if you want to get, the modern results come by using self-concordance. So if F0 and the log barrier are self-concordant, then TF0 is self-concordant for t bigger than 1. And TF0 plus phi is self-concordant for t bigger than 1. And we'll get to that a bit later. But let's just look at some examples and see how this works. This is the dual of the problem you're solving on your homework. But it's an LP with 100 inequalities and 50 variables. And this shows you the number of Newton steps. By the way, the computational effort is simply measured, the unit is the number of Newton steps, period. So that's the cost, is Newton steps here. So the number of Newton steps here is plotted here, and this gives you your duality gap. And so it's plotted with one of these staircase things. And a staircase thing, it says that the width of a stair is exactly the number of Newton steps required to carry out that centering. The height of a stair is exactly the reduction in duality gap obtained when you finish recentering. Now, in this method, the duality gap simply goes down by a factor mu. So since that's a log scale, the height of the steps for each of these plots is identical. And in fact, it's exactly equal to log mu or something like that, or whatever it is. It's something. It's a factor of mu down. So here's little mouse steps here. Oh, not even that mousy. I mean, you're doubling. But you can see everything. You can guess all sorts of things here. You asked about the Newton quadratic convergence and stuff like that. You can sort of see down here, you're taking like probably one or two steps. Maybe these are 2 steps each, right? So basically, you double mu, you do 2 Newton steps, double mu, 2 Newton steps, double t, do 2 Newton steps. That's this. Now you're making pretty good progress down here. And you can see down here, this is what you get. The weird part is here. This is mu equals 50. For mu equals 50, you see what's happening is the width of the treads are much wider because you're taking more Newton steps to actually recenter. But of course then, the measure of progress actually is duality gap reduction per Newton step. That's really what you want. Because when you start with a duality gap of 100 and you want to reduce your duality gap, which is your ignorance, by a factor of 10 to the 8, then somehow you have to make progress you have to reduce your ignorance by a factor of 10 to the 8. And you have to do that in some number of Newton steps or whatever. So, and you can see here, at mu equals 50, it's actually down. By the way, that number is like 30-something steps. That actually probably takes a little, this is probably a good time to stop before we get into all the horrible details of mu and t and self-concordance, all that. It's actually time to just take a moment and realize what this says. By the way, you see this picture? It looks the same if there's a million variables. It looks the same if this is a maximum entropy problem. It looks the same if this is a problem from finance, signal processing, image processing, machine learning. They all look like that. They look just like this. There's essentially no difference, okay? And it's completely independent of the size of the problem. It just looks like this, okay? Now this is really quite ridiculous because at mu equals 50, it means that with a total number on the order of 35 Newton steps, you've actually solved an LP to extremely high accuracy using Newton steps. So actually, let's just step back and think about what that means. First of all, it's quite ridiculous. The feasible set is a polyhedron defined by 100 inequalities and 50 variables. How many vertices does such a polyhedron have? How many? 2 to the 50. Okay, sure, yeah, sure, that's fine. Yeah, a lot. The answer is, if by that you meant a lot, then I'll accept your answer. And that's a good answer, 2 to the 50. Okay, the answer is there's a lot of vertices on such a polyhedron. This is a baby problem. There are a lot of vertices on that polyhedron, right? Okay, one of them, generically, is our optimal solution, okay? So what is insane is that this method has done the following. 35 times you stopped in the interior of the polyhedron, asked for directions, and were told to go in some direction. You then tried a step of 1. If you didn't like that, you backed off to a half, and then to a quarter. So somehow, after 35 times asking directions, you went from somewhere in the middle of this polyhedron in R50 to a point which is essentially optimal. Everybody see what I'm saying? So the whole thing is highly implausible. 35 steps, that's smaller than the dimension of the problem, if you think about it. I mean, there's 50 orthogonal directions you can go into, and you ask for directions 35 times. Since this big figure looks the same when there's a million variables, then it gets just totally beyond anything you can possibly imagine. And it looks the same, which is ridiculous. It means basically to solve a convex problem with a million variables, like 30 odd times you stop and ask for directions. And after 30 such steps, you have an extremely accurate solution. It's really quite ridiculous when you think about it from that point of view. So.
How would this compare to if you use something like the simplex method? For
Simplex method would also be very, very fast on this. So simplex method is, I mean, it's not something we're going to talk about, but simplex method is when you actually go along the outside of the polyhedron and you take an edge greedily. That actually works also stunningly well. So.
For each Newton step, the cost is a proportion of mu or mu squared.
Neither. Oh, the cost per Newton step. Cost per Newton step is depends on the problem, right? So in this case, what's the cost per Newton step for this one? You have 50 variables, 100 inequalities. So you have to, I mean, yeah, it's something like n cubed, but in fact, what you'll actually find, believe it or not, is forming the engine is like more expensive. So it would be 100 times 50 squared. Yeah, so that's what it would be. So the cost of a Newton step is 100 times 50 squared. I mean, I don't want, does someone want to calculate? I guess, is Yang here? Or someone? Someone want to calculate what the cost is? How fast can you do? Let's figure out how long this actually would have gone down. Let's say written in C, calling LAPACK directly. So it's like 50 times, it's 100 times 50 squared. Let's just say that's what the complexity is. Should we just round it? Should we round it up and make it like 100 cubed? Sure. Let's make it 100 cubed. That's 4 times mud. That's okay. Let's make it 100 cubed. Just roll round up. So 100 cubed. How long does it take to solve an equation with 100 linear equations, 100 variables? I keep coming back to this and I'm going to keep coming back until people start answering the right way.
millisecond?
Thank you. Millisecond. Okay. Sub-millisecond. Okay. So how long did it take to solve this LP? 30 milliseconds. Okay. So, by the way, there's not a lot of people who appreciate this fact because, well, why not? I'll go off on a weird tangent. Why not? Okay. So basically, linear programming has been around since 1948 or whatever, and it's usually associated. People imagine. I mean, if you close your eyes, you picture like a Cray computer and some guys wearing like white lab coats, and and it's a machine that costs $1 million, and it's some expensive thing, and you imagine. You would use it for, I don't know, scheduling the airlines tomorrow, pricing a derivative, designing a nuclear weapon. You think of these big iron, you know what I'm talking about? That's kind of what you think. That's how a lot of people think of linear programming, especially if like you're an older professor or something like that, and that's kind of when you learned about all this stuff, right? So that's your picture of what solving an LP is. Right? And it's cool. I mean, that is how United schedules their airlines tomorrow. In fact, that's how they do it. I mean, roughly. But, okay. And in fact, yes, that's how you optimize portfolios and things like that. But I think what happened since then is, well, let's say Moore's Law made computers, I don't know, 10 to the 8 times faster or something. And there's been also algorithmic improvements. So the idea that you can solve an LP of this size in milliseconds, I think really hasn't really hit people yet. People don't know it. People who do control don't know it, for example. They sure don't know it. They still think you can carry out like 4 floating point operations like per control calculation. They don't know it. And people who do this stuff like over in our own department here, they don't think about doing things like this. So this is important for embedded applications. So, all right, enough of that. We'll move on. That was just a big aside. Okay.
So what
Yeah.
caused the mu equal 150 case to take longer? Was that just because
Yeah.
of all the haphazard?
You got it. No. The trade-off, it makes perfect sense. If mu is too small, what's happening is this. You're making not enough progress each centering step. The centering steps are easy, but you're not decreasing your gap fast enough. When mu is too large, you've bitten off more than Newton can chew. And so what's happening now is when you finish a centering step, you've made a lot of reduction in gap. But what's happened is you're taking a whole lot of Newton steps. Now the cool part is that these two trade off each other, and you get this huge flat thing like this. It's not common to be something like this here, this flat. But the point is, there's a big choice of, this is not a parameter that needs to be tuned. Let's put it that way. It's usually set and then forgotten. There's a question?
Is there ever an advantage to making mu not constant?
problems I can.
Oh yeah, yeah, absolutely. Yeah, I know you keep coming back. No, the truth is, we're doing I'm showing you, and you will in fact code before next Tuesday, an amateur version of this. It will be a very small number of lines. No, fancy ones don't update by a fixed parameter mu. You're exactly right. They actually have a very complicated way that, by the way, for LPs and QPs works amazingly well. It's called like a Marotra predictor corrector thing. But the shock is that something this stupid really works, like really quite decently. So yes, sophisticated methods will actually will crank up T by some adaptive scheme. So yes, that's correct. There was another question. Do you have one?
I was just going to ask how well that would work on a PIC.
On a what?
On a PIC? Like a small processor?
On a PIC. I don't know.
Okay.
But I mean, it wouldn't be, I don't think it'd be pretty,
Probably
I
get
think,
it to work.
I don't see why we couldn't do it. I mean, all you have to do is multiply, the entire thing is you have to multiply a matrix which is 100 by 50 by its transpose.
Right.
Or actually all you really have to do is a QR on it, that's all. So yeah, you could put this on an, ARM or PIC or I don't know, I guess. I don't know that people have done that. That'd be cool. Someone could do that next quarter as a project. Put some interior point thing on an ARM processor or something weird like that. For no reason, just because it would be cool. I don't know. Okay. All right. So here's a geometric program, a GP. So it looks the same story. And it's just the same. And then here's sort of what happens if you have a family of standard LPs. And then what's happening here is you're changing the size. So this is, what is this? Oh, hey, this is your homework problem. What do you know? What? Oh, that's interesting. Because you know what? Since all the code, it means Google will find the solution to your homework. But it doesn't matter. We all know that anyway. So anyway, this is what isn't this what you're doing? I think so. Yeah. So fine. So if you did it right, here's what will happen. You'll make something that looks like this, and then this is the most amazing thing that happens. It's this. Here's the number of what is M? M is the what is M? Oh, A is an RM. M by 2M. So there's two. This is the number of constraints. The number of variables is twice this number. Okay. So that's 20 variables, 10 constraints, 100 variables, 200 constraints. Did I say that right? Yeah, I reversed those. Anyway, you get the idea. That's 2,000 variables, 1,000 constraints. And here you generate a whole bunch of random problems and then solve them. And this is the number of steps required to reduce the duality gap, probably to 10 to the minus 6 or something. Or reduce it by a factor of 10 to the 8. When you look at this, you see something amazing. And that is that it's not growing. It just doesn't grow. So, and I can tell you a little bit. I'll just tell you a little story about about this. Well, I guess when these methods were first looked at, we'll see very soon. I mean, next lecture we'll see that the theoretical computational complexity says that the total number of Newton steps is less than square root m, where that's the number of constraints. Okay? And by the way, with a number out front, that's just like a number. It's not one of these mysterious, useless convergence proofs that has like Lipschitz constant and all sorts of crap that you don't know. It's just a number. So it's going to be some number in front times square root m. That's the number of steps it takes, period, for these things. Now, if you're a complexity theorist, that you celebrate this because you say, well, there you go. You see it grows like the square root of the problem size. Each step takes, in the simplest case, n cubed or something. And so you'd have an order n to the 3.5, and you'd have a polynomial time party or something like, big celebration or something, right? And walk away. Now, what happened was after and by the way, that's the theorists, that's where they are right now. The complexity theorists will tell you it's the number of iterations grows like the square root. But after people seeing this on and over and over and over again, actually somebody finally timidly said, no, it clearly grows less than square root m. And somebody finally said, I don't know, fourth root. Then somebody said the log. And what's become completely clear is that it grows like this, O of 1. Okay, that's become, as an empirical fact, that would appear to be the case. And in fact, to be much more specific, it appears to be between 20 and 80 steps for all problems. So let that sink in for a second because it's quite ridiculous. And it's actually the essence of, it's why these interior point methods, and you know, we'll look into them and we'll look at centering and duality gap and complexity and all that. But I don't want the main message should not be lost in all of that. The main message is this. They take between 20 and 80 steps. It's a problem in finance, machine learning. Doesn't make any difference. The size doesn't make any difference. It's about between 20 and 80 steps. And actually, I think I may have told you this earlier. Maybe on the first day I told you this, but now you know more about it. We had a talk last year by a guy named Jack Gonzio from Edinburgh. And he came and solved some giant finance problem with 1 billion variables. Okay? It was dense, by the way. It had a tree. No, seriously. It was some big tree. It had some structure. But this was not a small problem. Let me just say that. It wasn't super sparse or anything like that. It had 1 billion variables. So he solved it. We're like, well, how did you do that? He had some room with it. He had a blue gene, you know, whatever. He had the whole room full of like compute, you know, thousands of processors and all this kind of stuff. And I said, what algorithm do you use? And he goes, same one everyone uses. So he just, by the way, not quite this. He used an adaptive step size, but it's not a whole lot different. It's basically this. It's basically what you're going to write. It's a billion variable problem. And I said, well, how many steps did it? I said, well, how did you pick the parameter value? He said, just the same everyone uses. You know, it doesn't matter anyway. So I said, how many steps did it take? He said, 21. So basically, I mean, that's a single point. Oh, now, I think I mentioned this earlier. It took 21 iterations. Now, by the way, each iteration took like several hours, and the lights in Edinburgh dimmed when each iteration was carried out. Well, I mean, it's solving 1 billion variables with a dense system, blah, blah, blah. But the point is on some giant room full of computers, right? With a big, 12 kilovolt three-phase thing going in for a while. But the point was, this thing, at least that we have one point way out here at 10 to the 9 provided by our friend. And, well, this is using our unsophisticated methods. The sophisticated methods are down here at the 20 level, although that hardly seems to matter. So, question?
This technique, like if he's running in a room full of computers, does this scale linearly with the number of...
No, his was not a fully dense, it had structure. In fact, it was an event tree. He was doing stochastic programming for some finance problem or something like that, and it just expanded the event tree out like 15 steps or something. That'll give you 1 billion variables. So the question is how parallel... Well, actually, let's talk about if you profile one of these, what in fact, if you run an interior point method, in fact, the one you're writing right now, what actually will it be doing? I mean, yours will actually be spending a lot more time doing interpreted overhead than actually doing any actual computing. But if you scaled yours up big enough, you do 20 steps, what are you actually doing in each step? What is it?
Linear system.
You're solving linear systems. You're solving a Newton. You're computing a Newton step. Line search and stuff like that doesn't cost anything. So you're solving. So in fact, the correct thing to say is if you want to solve a convex optimization problem, you're going to solve 20 linear equations. All right, 80, whatever. Something between 20 and 80 linear equations. Period. That's all you're doing. So, and you can use any method. I mean, we've just looked at the most simple things, right, where you use a Cholesky or something. I mean, if there's some structure right under your nose, like, Bandit or something like that, of course you should exploit it. But then there's whole worlds of solving like huge linear equations that we haven't even touched on, but exist and can be applied. So, okay. Any more questions about that? That was just like a weird, I don't know, detour. Okay. Let's talk about feasibility in phase 1 methods. So, in fact, you'll have to do this. So the feasibility problem is you want to find an x for which fi of x is less than 0. Well, I tell you the truth is you really want to find something like that if you want to initialize a simple interior point method like the one we have. So this is what you want. So there's lots of ways to do this. They're actually all kind of cool. The standard tricks, these go back to 1948 or something like that. I mean, the standard trick is to solve phase 1 by solving a similar problem. So here's what you do. You solve this problem. This is the most classic one. You have a new variable s, and you say fi of x is less than s here. Ax equals b. And you minimize s. here in this problem. That's a convex problem too. However, for this problem, I can always find a strictly feasible point. Well, sorry, provided I know any x that's in the domain of f and satisfies ax equals b. I choose whatever x I like. Okay? Not feasible for the original problem. I mean, a lot of the fi's are way bigger than 0. And then I find the max of the si's, and I take s equal to that max plus 1. And that's now strictly feasible, a strictly feasible point. I apply a barrier method or SUMPT to this thing. And then I can put in logic that says this. If s ever gets negative, just quit, because that's good enough. You've actually produced. And then you would drop to phase 2. Phase 2 would start from there and would actually then optimize the original objective, which would be F0. F0 is not in here. Everybody see this? So that's the idea. So this is the standard. Now, if you're minimizing this problem and you minimize it, and S star is positive, you actually now have a proof that the original problem is infeasible. And in fact, by taking the dual point found from S star here, by solving this problem, actually is a certificate. It's a certificate establishing that the original system of inequalities is infeasible. Okay? And there's one thing where the results are ambiguous, and that's when P star is 0. Okay? So that's when you're right on the boundary. It says that the problem is, let's see, it means it's feasible. Well, it could be all sorts of sick things could happen. It means the problem could be feasible, but not strictly feasible, and so on and so forth. Okay. Now, by the way, let's talk about how you imagine this is going to work. So let's do that. Let's imagine if the problem is feasible, this will work perfectly. S will keep going down. At one point, S will become negative, and you terminate. You put logic in there to terminate. So you call your barrier method with a string that says phase 1. And it knows then stop not when your duality gap is low, but stop whenever S is negative and quit right there. However, suppose it's infeasible, and let's see what happens if something's infeasible. These are Fi of x here. And let's say I start with a problem like this. I don't know why I'm drawing them up like that. I don't know what that was. Sorry. Do it again. All right. So here's 0, our critical point. Here's Fi of x. Here's a bunch of inequalities that are satisfied like that. And here's a bunch that are violated. Okay? Now, this phase 1 method puts S over here. It puts a bound above these guys. That's S. And it starts pushing this thing to the left, right? Is that? Yeah, okay. I was checking if that was the left. Yeah. That's pathetic, isn't it? Oh, well, all right. So you start pushing this to the left. And of course, if you ever push to 0, then they're all on the left. You exit and you jump to phase 2. Okay? Now, what do you mean? Suppose the problem's infeasible, though. You're going to push and push and push, and you're going to stop because you can't find a point that has all the Fi's negative. When you stop, what do you imagine is going to happen? Suppose when you stop, S star is 1. What do you think what do you think this plot is going to look like?
Bunch of functions.
You got it. A whole bunch of constraints are going to be violated by 1. Okay? So a lot of constraints are going to be violated because when you start pushing points like this, right, they'll pile up and a bunch will pile up and you'll keep pushing, it'll get harder. Then you come up against a wall and you stop. Oh, by the way, what's the force that you have to push with it? The Lagrange multipliers, right? It's the sum of the Lagrange multipliers. Mechanically, I mean, that's exactly what it is. So you push and push and push, push, then you hit the wall. You hit the wall and a whole bunch of things are violated. Okay? Well, you answered your question. Your problem is not feasible. But there's actually there are other very interesting variations on this, and I'll talk about one, and then we'll move. We'll quit, actually. Let's see. So the sum of infeasibilities method works like this. I introduce a private. Oh, by the way, you can think of S as sort of like a little. The interpretation of S here is you're looking for a point where Fi of x is less than 0. That's what you're looking for. So you say, well, look, I'll give you a little extra slack, a bonus. You know, you don't have to do 0. You can make it less than 7, and then 7 gets pushed down. Okay. So here, though. Everyone gets their own private little slack thing. By the way, if we've seen this before, this is the beginning of the story on the support vector machine. Okay? Actually, it's the beginning of the story on a lot of things. So what you do is this. Everybody gets their own little slack. If this slack is 0, it means that inequality is happy. It's satisfied. And you want to minimize the sum of these infeasibilities. Now, already you should have all the neural connections. Before you even do this or anything like that, you should have a feeling for what's going to happen when this is infeasible. What's going to happen in this case is, this is a heuristic for solving the problem. Please find me a point that violates as few of the inequalities as possible. Okay? This is a heuristic for it. That's how the support vector machine works. That's how all these things work. Okay? When you solve this problem, here is what happens. When you solve this, and this is you have 100 infeasible linear inequalities and 50 variables. It's infeasible, and this is what happens when you. This is plotted backwards, I guess, but these are supposed to be positive. When you push these up here, here's what happens. You get to the point, and basically, most inequalities are violated. So this is the basic phase one. When you do a sum of infeasibility, you identify there's only 21 in the end that are violated. Is 21 the minimum number of constraints that can be violated? Who knows? No one knows. But it's a heuristic for violating just a few. So this has a lot of this would have lots and lots of applications. If you're doing engineering design, for example, and you have a whole bunch of inequalities, and it's infeasible. Of course, the main message to tell somebody, which is useful, is sorry, but your specs can't be met. That's the most important thing. But after that, someone says, well, gee, thanks for the bad news, but can you tell me which ones I should relax? Which constraints do I have to go back to somebody, the specifier, and actually beg and grovel for more from, right? That's what basically happens. So in a normal phase one, everything is violated. You don't really have an idea of which were the ones that were most violating or something like that. In this case, you'd actually go back and zoom in on ones that are I mean, you don't know this is the minimum set of violations, but it gives you much more information. So, okay, we'll quit here.